On this episode of MRI Physics Explained, math. Gross. But wait, this isn't just any math. We're going to cover the most important equation in all MRI physics, the MRI Equation. I'll be honest with you, this is hideously complex, but it's so important because this is the key to understanding our next talk on K-space. No slide rules or TI-83s needed. Let's focus on the big picture in this critical episode of MRI Physics Explained. Hello and welcome everybody as we progress through this lecture series describing how magnetic resonance imaging really works. As a refresher, last episode we initiated this cycle of understanding with an in-depth look at the Fourier series and Fourier transform, what it is mathematically, but more importantly, what does it mean visually? The link is above if you need a refresher, and I highly recommend you familiarize yourself with it before proceeding. But at the end of the lecture, we dropped a rather unbelievable claim. In this Fourier transform process shown in the picture, we claim that our raw MRI data is in fact frequency data, or planes of frequency in our two-dimensional Fourier transform. And as a result of this, to generate our picture, we actually perform an inverse Fourier transform on this raw data, producing the images we've come to know and love. Now I admit, this is an outrageous claim. How can the raw MRI data represent frequencies? And why would an inverse Fourier transform give us our image when the only thing we've ever been taught is that we perform a Fourier transform and get frequency space? This classic picture that has thrown learners into unfathomable confusion across millennia, myself included. So if we're going to buck the trend of the traditional MRI physics teachings and make such an outrageous claim, we're going to have to back this up with some cold, hard math, which brings us to today's topic. The MRI equation. We're going to derive the equation that turns nuclear magnetic resonance into magnetic resonance imaging, and in doing so, open the door to understanding K-space. Now this is going to involve high-level math, but as always we're going to focus on the big picture, so hopefully all can follow along. And this talk is based off a paper by Drs. Bruce Rosen and Lawrence Wald from the Harvard-MIT Division of Health Sciences and Technology. Thank you for making your work open to all, and I'll post the link to the paper in the description below. With that, let's get started. So here is our target. I told you we're going to be performing an inverse two-dimensional Fourier transform to get our picture. So whatever formula we derive has to eventually match this form of a 2D Fourier transform. The inverse part will come later. What this formula essentially states are that the frequencies in our picture, denoted by this capital F at point UV, equals a point xy in our real image times this funky looking term integrated at all points xy within the slice. We'll keep this formula in view throughout the lecture to see the progress as we develop our own formula, and a good place to start is defining the coordinate system our formula is going to use. If this is our slice, we know we're going to have our baseline magnetic field B0 going throughout the whole body and this slice. This B0 field allows us to build our little magnets within each voxel of the slice as previously covered, all initially aligned as shown here because we have yet to energize the system with an RF pulse. Now we need to add some axes to our slice. Let's put the x-axis here and the y-axis here. Now your intuition may be to number these axes in the standard way, starting from 0 in the bottom left corner and increasing as we go to the right and upwards. But in MRI physics, as usual, things are a bit more complicated. Remember that all these little magnets are going to start spinning at some point, and this spin rate is predominantly determined by the baseline magnetic field B0, as well as any magnetic field gradients we apply across our slice, most commonly a gradient across the x-axis, as well as another gradient across the y-axis. Now I want you to notice this peculiar voxel right dead center in our slice. Notice that this is where these gradient fields equal 0, the point where they cross the background B0 value, and therefore, no matter whether one gradient is on, or both are off, this voxel will only ever see the main background magnetic field B0. We call this point the isocenter, and it's important because it provides a fixed point of reference. as all of these individual magnets start rotating at different rates, and we're trying to mathematically figure out how in phase they are, we can always go back to this voxel and say, hey, this is what these should be rotating at if we left the whole thing alone and didn't apply gradients. So let's put the origin of our x-axis here, with x equals 0 being in line with our isocenter voxel, and accordingly, if we move to the left at this point, we will head in the negative x direction, and if we move to the right of this point, we'll head in the positive x direction. Same idea with the y-axis. We'll set our origin y equals 0 centimeters in line with the isocenter voxel, and if we move up from there, we'll be headed in the positive y direction, down will be the negative y direction. Is everybody okay with this? So going back to our formula, the target format for whatever equation we end up with must match this overall structure of a two-dimensional Fourier transform. But first, if you enjoy these videos, consider liking and commenting, following us on social media, hit the join button to see ways you can support us further, and click that subscribe button below. Okay, back to our scheduled programming. To start, let's break down this whole process into the most basic relationship we know. No matter what we do in MRI imaging, at its core, what we measure is signal, S, coming from the entire slice over a time period, t. Signal as a function of time. So this brings about a critical question. What will our signal S of t depend on? What are the factors that determine our signal strength? In other words, where does this signal come from? Ultimately, it comes from the proton density within our slice. The number of protons within our slice determines how big of a magnet we can build within it, which then determines the maximum amount of signal we can generate. But we can be a little more specific here because mathematically we want to know what's going on at the individual voxel level. So we'll say that the signal depends on the proton density, rho, at each point xy within our slice. Is that all? It turns out the other major factor is how in phase or in line the magnet within each voxel is relative to our reference voxel, the isocenter. What do we mean by this? As we've covered in prior lectures, we have our slice of the body we wish to image. It's filled with randomly oriented protons, and when we apply a large magnetic field, B0, we grow these magnets within each voxel of the slice, all nicely aligned with our B0 field. We then apply an RF pulse to energize the system, and then they begin precessing in concert with one another, generating signal within our receiver coil. However, over time, and in the absence of any other magnetic fields, some of these magnets will start spinning at different rates as time goes on, and the more and more out of phase they get with one another, the more our signal decreases and is eventually lost, what we call T2 decay. Now we cannot control this process of T2 decay, it's going to happen no matter what we do, and in fact, we want it to happen. This is what gives our picture its contrast. But if we're going to model this mathematically, it's critical that we include anything that we may do to increase or decrease dephasing within our slice, because that will directly affect our signal. Let's explore this a little further. We in fact have a bit of a problem here. As we know from previous lectures, we'll be applying what are traditionally called frequency and phase encoding gradient magnetic fields across the x and y axes in order to produce our picture. Let's look at what happens to the magnets within each voxel when we apply these gradients. Let's apply this gradient field g of x across the x-axis, say for 1 millisecond. Given this changes our magnetic field from low to high as we move from left to right across the slice, the little magnets we've created within our voxels will therefore rotate at different speeds according to our Larmor frequency, from slow to fast, moving from left to right, following the direction of our gradient field. This will therefore cause dephasing as shown. And as we know, the less in phase these magnets are, the less signal we generate. What happens if we apply this gradient field for a longer duration than the previous example? Let's say for 4 milliseconds instead of 1. As logic would have it, we'll get even more dephasing across the x-axis of the slice, decreasing our signal even further. So we've established an important relationship. The longer we apply this gradient field across the x-axis, the more dephasing we cause. In fact, if you've been following this lecture series, you may remember we stumbled upon this idea in our Gradient Recalled Echo lecture, and I hinted at the time how profound and important this concept is. What about when we apply our phase encoding gradient, the one across the y-axis? Does this cause the same problem? Let's just rotate these to a new starting point for better visualization. If we apply this gradient field across the y-axis for 1 millisecond, what happens to the phase of the magnets within each voxel compared across the slice? What do you know? The exact same thing. We cause dephasing within the slice, decreasing our signal, and like before, the longer this gradient field is applied, the more dephasing it will cause. So the big takeaway from this exercise is that anytime we apply a gradient field, we cause dephasing and decrease the signal generated by the slice. The amount of dephasing depends on the strength of the gradient field, Gx or Gy, whichever one we choose to apply, and the length of time the field is applied. Now this is a little confusing because we're really talking about two independent time events. So if we're applying the Gx field across the x-axis, we're going to use the traditional time symbol t. If we're applying the Gy field across the y-axis, we'll use the lowercase symbol tau. Because these are independent, we have to use different time symbols mathematically when describing them. So back to our equation, I hope you can now see that our signal will depend on the proton density within each voxel. This determines the maximum amount of signal we can theoretically generate, as well as how in phase our rotating magnets are relative to one another, which determines how much of that maximum signal we actually see. Let's rewrite this second point in more mathematical terms. Delta phi, the change in phase relative to our isocenter voxel, will be a function of the voxel location within the slice xy and the amount of time these voxels experience different rates of rotation. This gives us a nice starting point for our formula. Now, as we've covered before, the total signal we measure, S of t, is going to be the sum, denoted by these two wavy lines, of our object in question, in this case the signal at each point xy coming from within our slice, dx dy in mathematical terms. Okay, not bad. Comparing our very early formula to the goal formula above, you can already see there's some similarities here. Now we have to decide what we're actually trying to solve for in this equation, and it might not be clear at first. Remember that we experimentally measure our signal over time, S of t. This is our raw MRI signal that we record, and is not unknown to us. Furthermore, we're going to keep refining this change of phase term. So our goal is to actually solve for this proton density term, rho at point xy within our slice. We're trying to mathematically generate an image from this raw signal measurement, and that image will ultimately depend on the distribution of protons within our slice. We can select parameters to accentuate or de-emphasize the signal generated from this distribution, what we call the contrast of the image, but that cannot exist without this foundational source of the signal. So in order to solve for rho xy, our proton density, we need to develop a formula to more accurately describe this term, delta phi, how much phase shift each voxel experiences relative to our isocenter voxel. So let's do just that. If delta phi at point xy in the slice and time t equals the cycles of phase shift from isocenter, this will be equal to our base precession from our main magnetic field B0, which equals the gyromagnetic ratio gamma times the strength of B0 times t, the amount of time the rotation has been going on. If our voxel's magnets are rotating at a certain angular speed, then we need to know how many seconds this has been rotating in order to figure out its position along a circle at that time point. Remember, precession, our angular speed, is determined by the Larmor frequency, this extremely simple formula that mainly relies on the magnetic field our protons experience, covered in the very first lecture. So this will be the base precession rate of our magnets across the slice. But wait, we need to account for any gradient magnetic fields we apply, as these will change the precession rate and cause dephasing as covered earlier in the lecture. Let's start with our gradient field g of x applied across the x-axis. The precession caused by gx will equal the gyromagnetic ratio gamma times the magnetic field applied gx times the position x within our slice times the amount of time t this field is applied. Likewise, the precession caused by our gradient field gy across the y-axis will equal the gyromagnetic ratio gamma times the strength of the magnetic field applied gy times the position y within our slice times the amount of time tau this field is applied. Now this seems a bit of a mess. Can we really just add all these together? Let's quickly perform a unit analysis to make sure it all lines up mathematically. This is one of my favorite tools to figure out what's going on in complicated equations. Let's start with the base precession. The units of gamma are megahertz per Tesla. Our main magnetic field B0 is measured in Tesla, and time is in seconds. If we multiply these units out, the Teslas will drop out. We then need to define what a megahertz is. 1 hertz is equal to a cycle per second. Forget about the mega part here, it's just a constant, and we're really only worried about the units here. With the addition of this term, you can see that the megahertz drop out. And furthermore, the seconds drop out, leaving us with cycles. So this checks out. If we plug in values to this formula, the end result is going to be the number of cycles of precession each voxel has experienced given the time period t. Let's do the same thing with the other terms. The precession contributed from our applied gradient field gx will follow a similar pattern, but notice instead of b0, we have this more complex term g of x times position x. Well, from the units of gx, we can see that it represents a magnetic field strength measured in Teslas that varies depending on where we are along the x-axis. To get what the strength of this g of x field is, we simply times it by the distance along the x-axis we are from isocenter. If it's to the left of isocenter, it'll be negative and subtract from the baseline B0 field according to our coordinate system. If it's to the right, it'll be positive and add. And if it's at isocenter, it equals 0. So let's go through the unit analysis like before. The Teslas cancel out, as do the centimeters. Now we have to define what a hertz is again, which allows us to cancel out the megahertz terms. The seconds then cancel out, and we're left with cycles of precession. And for the gradient field gy applied across the y-axis, the exact same thing, except since we're now varying the field across the y-axis, we need to know what position we are y centimeters from the isocenter, and how many seconds this field is applied using the symbol tau since it's an independent time from the one we use for gx. From here, the Teslas cancel out, as do the centimeters. We define a hertz once more. The megahertz terms drop out. The seconds drop out. And what are we left with? Cycles. So yes, in fact, we can do this. We can plug in values for these terms, which we decide when designing and operating our MRI machine, add them all together, and can predict the amount of phase shift each voxel will experience anywhere in the slice from our gradient fields. So the amount of phase shift at point x, y, and time t in the slice equals the baseline precession from our main magnetic field B0 plus the contributions from our gradient fields gx and gy. Now for those paying close attention, you may be wondering why this function is only dependent on one time variable, t. What about tau? Well, not to get ahead of ourselves, but tau is really describing the time we blip on what is traditionally referred to as our phase encoding gradient, and is really treated like a constant for each cycle of our pulse sequence, but more on that to come. So as you remember, this is the formula so far for the amount of signal recorded from the slice. So let's plug in this new term into the appropriate location. This gives us this messy looking formula here. Let's do a quick check to make sure we haven't made an error. If we apply no gradient fields, meaning gx and gy equal 0, these terms go to 0, and we're left with only the baseline precession b0. It seems to check out. So here's our formula as it stands, and notice this term we just derived is in cycles, degrees, a phase shift. Now, as some of you may remember from high school math, degrees are kind of basic. What we really want to describe is our rotating magnet's position along a circle, and in a way that works well with Fourier transforms, and it turns out we have the perfect formula for this. We need to apply Euler's formula. Yes, it is pronounced nothing like it's spelled. Euler's formula relates a vector's degrees to its position along the real and imaginary axes of a unit circle. I know it introduces the imaginary number I into the mix, but unfortunately they are inescapable in many useful things like Fourier transforms and signal processing. So as the famous prayer goes, grant us the serenity to accept the things we cannot change, specifically imaginary numbers. But what we can change is our formula below. If this term represents phi, our degrees of phase shift, we can plug it in here to put this in more Fourier transform friendly terms, giving us the following. Notice that we had to add a 2 pi to convert one cycle, 360 degrees, into 2 pi radians. Now this first term, gamma times b0 times time t, is sometimes referred to as the carrier frequency, which is important for signal transmission, but not for signal demodulation, which is what we're doing, converting our received signal into a picture, so we can actually discard this term. This leaves us with the following. And let's now compare this to our original target formula. Wow, this is getting amazingly close, don't you think? Let's do a few more tweaks and we'll have it. Let's simplify these inside terms. Let's take this first one and combine this gamma, gx, and t into one term for simplicity. We'll call it kx. We haven't changed the values, just simply lumped the terms under a single variable. Let's do the same for these terms, calling them ky. If we substitute these new terms back into the equation, we get a simplified looking version of the formula below. Alright my friends, we're almost there. We can take advantage of one more important relationship, the conjugation property. If our signal s of t is real, which it is, so just say yes, we can apply the following confusing looking relationship with regards to Fourier transforms, which allows us to swap this term s of t with the following term, our frequency space data points kx and ky. This is one of the more challenging relationships to understand and requires thorough knowledge of all the terms and notations for our 2D Fourier transform, but by making this allowable swap, check out the form of our derived equation now. It's there, we've done it. Now to solve for our proton density at point xy in the slice, all we have to do is take the inverse Fourier transform of this k-space data. The proton density will equal the inverse Fourier transform of our signal, which represents this frequency data kx, ky. This lengthy, some would argue painful, derivation is necessary because it tells us how to build an image by taking the inverse Fourier transform of our raw data, which needs to contain different combinations of these k values, our magnetic field gradients applied across the slice's x and y axes over time. If your mind is telling you k, why is this so familiar? Could it possibly be that thing we always talk about but never makes sense in the traditional MRI framework? Well, on the next episode of MRI Physics Explained, the time has finally arrived. The stage is set for the talk you've all been waiting for, K-space. We've developed a mathematical definition and understanding of these K values, but what does this actually mean in practice? All of this and more on the next episode of MRI Physics Explained. If you enjoyed this lecture and haven't yet already, consider liking and commenting on the video, following us on social media, subscribing to the channel, and consider becoming a member and joining for special perks. And that will do it for today's lecture. Until next time, this is Dr. T.E. signing off.